All right, gas laws. So, our gas laws, what are the conditions of STP? Remember, STP is standard temperature and pressure. That's again how we know that there's 22.4 liters equal to 1 mole of a substance. But the condition standard temperature is 273 Kelvin, which is equivalent to 0 degrees Celsius, right? And then our pressure is 1 atmosphere, or it could be any of the above: 14.7 psi, 101.3 kilopascals, 760 millimeters mercury, 760 torr. Which one am I missing? You get the gist, right? So it's just all the same value, just different units, right? So for the next ones, again, we are knowing that Kelvin is a scale that we use in this unit, and there's just no negative temperatures because that shouldn't be able to happen, right? So you take your degrees Celsius and you add 273 to it, and when you get to 0 Kelvin, that's absolute zero. There's nothing lower than that. It's where all things cease to move because it's so cold. So convert the following. So we have Celsius, of course. This is going to be plus 273. That gives us 317. Now you have Kelvin, so you go backwards. So you're subtracting. That gives us 27 degrees Celsius. And 0 degrees Celsius is just 273 Kelvin. How many atmospheres are in 750 millimeters mercury? Well, 750 millimeters mercury are... I know that there are 760 millimeters mercury for every 1 atmosphere. And then I go through and I get 0.99 atmospheres there. All right. And then we do the same thing. We start with atmospheres here. And we convert. I know that for every 1 atmosphere, we have 101.3 kilopascals. You'll be given these conversions as well, just like you'll be given other conversion factors too. And we end up with, I believe, 12,764 kilopascals, if I read that correctly. All right. Down here, really what this is trying to tell you is out of the 3 gas laws that we have, right, Boyle's, Gay-Lussac, and Charles, there is only one inverse relationship, and there should be a box here, but this is inverse or indirect. And as one goes up, the other goes down. The only one that had that happen was Boyle's law, which is the relationship between volume and pressure. Right, as one goes up, the other goes down, so on and so forth. And the other two, it doesn't necessarily matter what you put where, but we did have, actually it does, because volume is not directly related to anything else other than temperature here. So this would be temperature. This would be temperature and pressure was the other relationship with those variables. And of course, plugging those in, this was Gay-Lussac, and Charles, proper name. You don't just put the parenthesis or the apostrophe. But this was a direct relationship, and this was also a direct relationship there. And we are good to go. So we use our equations that you will be provided to work through these problems. And realistically, the only 2 that you need is our combined gas law and our deal, right? Because the combined gas law takes all of these guys' laws and just smushes it together, and then you can eliminate anything that you are told is constant or is just not mentioned in a problem at all. So for something like this, a student cools that liter sample from this to this, right? So I'm dealing with temps, and of course I need to make sure that my temps are always in Kelvin. So I need to add 273 to those. I get 358.5 here, and I get 298 here. And then this is T1 and T2, and I know that because that's what I say I'm cooling it from this to this, right? Context clues. This is my V1, that's liters for volume. I'm looking for new volume, which is V2, right? And so what we can do is we can say, because pressure remains constant, our usual go-to would be to set something up that looks like this, right? Where we have to inventory what we're given and what we don't know. So we know that our temperature or our volume is 7.6 liters. Our volume is, our temperature is 358.5 Kelvin, and 298 Kelvin was the temperature too. And we are looking for the new volume because pressure remains constant. We can actually just get rid of pressure altogether. We don't have to worry about it. And what that helps us with is that when we do our combined gas law, that looks like this. Oops. Getting rid of the one that we don't need allows us to just have what would be Charles' law, right? And so that's the cool part about our combined gas law and knowing what's constant, what's not. So the easiest way to go about these problems with these numerator and denominator on each side is cross multiplication. You just plug in what you know. So I know that V1 is 7.6 liters. T1 is 358.5. V2 we do not know, and there's 298 Kelvin there. I know that I'm going to crisscross the multiplication, and I end up with on one side 2,264.8 equals 358.5 times V2, and then we divide both sides by 358.5, and we end up with 6.32 liters. All right, let's see here. Doing something similar, I'm going to just label everything like this from the start, and then we'll go through what we actually need to use and what we might not need to use here in a sec. So Lucy goes scuba diving, and she very, very adventurous. On the boat, the temperature is -2 degrees. Could not be me. -2 degrees Celsius. And we, of course, know that that needs to be converted. So we add 273. That ends up being 271 Kelvin. And the pressure in her tank reads PSI. Now, it's important to note that because we are going to be dealing with a multiple sides, like a combined gas law problem, not ideal, PSI can stay PSI. That's the beauty of that. When you have multiple, remember, just like we kept milliliters the same for the dilution problem. So we're going to keep PSI as our primary unit here for pressure because, again, it does not matter since it appears on both sides. Her tank reads 2,900 PSI. So 2,900 PSI is her initial pressure. And that was at 271 Kelvin. When she is, though the water is warmer than the air, so she dives in and watches the pressure rise. So the pressure rises, which means it's a new pressure. So what must be the water's temperature when Lucy is diving? It shouldn't be there. It says nothing about the volume, and also because it's a tank, an air tank, that volume is pretty fixed, right? So that means that the volume is what we can ignore here. and we're looking for T2. So using our combined gas law, what we can do is we can confidently remove volume, and we are left with Guy-Lussac's law, right? And now we just plug in what we know, 2,900 divided by 271 equals 3,000 divided by T2. Again, cross multiply. Cross multiply there, cross multiply there, cross multiply everywhere. Let's see. We get 813,000 equals 271. No, sorry. Sure doesn't. 2,900 times T2. Divide both sides by 2,900. And we end up with a final answer of 280 Kelvin. Does that check out? Sure does, because the temperature should be a little bit higher since the pressure increased, right? It's warmer than air. So that checks out. And then over here we have a volume, we have a pressure, we're asked to find another volume, we have another pressure, so that's how we know this is combined gas law, not ideal, or it's one of our other individual gas laws. So I like just assuming before I even read that we're going to have all of these and be pleasantly surprised when one of those we don't have to worry about. Gas occupy, so that's telling me that currently is happening at 659 millimeters mercury. 659 millimeters mercury. I don't know the new volume if the pressure rises or has risen to 885 millimeters mercury at the same temperature. So even if this part wasn't even there and we didn't see temperature, then we could just assume it's constant. But because they're telling us, we know for sure that we can get rid of it, which means that we end up with just Boyle's law. Let me double check that. Okay. Just Boyle's law, because the temperatures, as you can see here, when you get rid of them, we don't have a denominator anymore, which is nice. So we just plug those in. 659 times, that's going to annoy me, times 3.5 liters equals 885 millimeters mercury times V2. All right, so you simplify, you get 659 times that is 885, which equals 885. Holy cow. And you divide both sides by 885. And of course, you're going to end up with... oh, I'm sorry. I misread that. Let's delete these. Let's see what 695 is. 695 times 3.5 gives us... that would have been confusing, huh? 2,432.5. Now we would divide both sides. And there we go. And our final answer should be... Come on. Our final answer should be, I believe, 2.61 liters. And does that make sense? And because it's Boyle's and it's pressure and volume, those are indirect. So as our pressure increased, we see our volume went down. That checks out. All right. Now we're going to get into our ideal gas law, right? An ideal gas law is PV equals nRT, where R is a constant of 0.0821. And of course, that is liters, atmospheres per mole Kelvin, right? Those are the obnoxious units, but that's what allows this constant to work. And that's also why we need to make sure that our pressure now is converted to ATM, and our volume is in liters and so on and so forth. Temperature, of course, has to be in Kelvin. And because I'm talking moles, as you can see, there's no moles in the combined gas law or any of the other three on their own. So that's how I also know that we're going to be dealing with PVNERT, or the ideal gas law. So P, V, N, T. I don't include R. We know what R is. But P is 1.2 kilopascals. However, that needs to be atmospheres in order for us to be able to use it. So we need to convert kilopascals to atmospheres. As you can see, I still have my mind on stoic. kPa go away. That's a cool rhyme. And we get 0.012 atmospheres. So there's our pressure. Our volume's already in liters. We don't know moles, and we do know temp as well as our R value. So we're going to plug everything in. Pressure's 0.012. Volume's 2.5. N is by itself 0.0821 and 300. Simplifying everything. Let's do this so that you have it. If we simplify, that would be 0.012 times 2.5. That's 0.03 equals 0.0821 times 300. That gives us 24.63. Divide both sides by 24.63. And we should end up with, I believe, well, let's do it just to be sure, 24.63. And we get, 0.0012 moles. And of course, that's of neon gas there. All right, so again, because we know that we're dealing with PVNERT, we have to be in the unit of ATM for pressure. We have to be in the unit of liters for volume. And of course, always Kelvin for temperature. So in this case, down here in the next one, this is actually going to be 273 plus that, which is 249.85 Kelvin. So there's that. This is the same pressure as above, so we already know that that's 0.012 atmospheres when you convert that. And we have liters, so we want moles again. P, V, N, T. We know R always, doesn't change. And we go to work. So that's that. I'm just labeling because that's what I do. 249. What was that? 249.85 Kelvin. That's a miserable 8. I'm trying to go too quickly, apparently. PV equals nRT. P is that. We're looking for N. We don't know it. R, we always know. And T, 249. Jeez Louise. Think before you write, Mr. H. All right, let's do this. Point that times, we already know that, 0.03. This one we will have change a little bit, 0.0821 times 249.85, 20.51, and divide. So you're like, probably, well, how do I know where to round? There's a lot of numbers there, and you rounded to you rounded to the thousands place sometimes, you rounded to the hundredths. I mean, the less you round, the better usually until the end. But, I mean, there's something like 0.512, it's going to be 0.513, and it's kind of negligible, so that's why I did that. And we should end up with 0.03 divided by 20.51, which gives us the 0.0015 moles of neon there. All right, so that was our gas laws, and we have one more section to go for our acids and bases.